Okay, so let's say we have a problem. You know that you have this circle here. This is the unit circle. So right here is 1. And let's say that you want to get the derivative of the circle. Well, that's a problem using our basic rules because the circle isn't a function. You can see that it doesn't pass the vertical line test, so it's definitely not a function. And this is written as an equation. Well, how do you do it? Well, you can tell that, you can draw a tangent line. You can see, obviously, that there should exist a way to find the tangent line anywhere on the circle because you can actually draw one anywhere. Okay, so one option is to rewrite the equation of a circle. If you solve for y, if you bring over the x squared, you would have 1 minus x squared, and then you get the square root of both sides. And so then you would get that y is equal to the square root of 1 minus x squared, but you have two. You have the positive and you have the negative. So the positive square root of 1 minus x squared corresponds to the top part, and the negative square root of 1 minus x squared corresponds to the bottom part. So, for example, if I wanted to find the tangent line at x equals to right here, pi over 4, sorry, not pi over, root 2 over 2, which is when the angle is pi over 4, then you can do it this way. So I'm going to let you guys do that because I want you guys to try that now. Get the tangent line at root 2 over 2. Now in this case you would use the positive square root because you're talking about the tangent line up here. But I'm going to use a different technique. And then when I'm done, then you guys can compare your answer with mine. And so what I'm going to do is I'm going to use a new technique called implicit differentiation. And implicit differentiation, it helps us find the derivative when we don't have a function written explicitly in terms of one variable. So it's for when we have an equation, with x's and y's or t's or p's or whatever, just kind of mixed in. So before we do that, I want you guys to remember something. You guys remember when we did, for example, when we used the chain rule? So we had, for example, let's say we have x squared minus 1 all to the 4th. And so we called this guy right here the inside function. And then we called this guy out here, this was the outside function. And so when you got the derivative of this guy, because it's a function of a function, the derivative, you had to use the chain rule. So you would, get the derivative of the outside, which is 4, leave the inside alone, and subtract 1. So x squared minus 1. But then you have to multiply times the derivative of the inside, right? Okay, so what I want you to pretend, and this is going to help the implicit differentiation method make sense. Think of this guy right here, the inside, as, let's call that y, And let's just emphasize that if I call this guy y, y is going to be a function of x, right? Okay, so if y is a function of x, so what I did right here is, if I rewrite this thinking of this guy just in general as y, I brought the 4 down, I left the inside alone, y of x, subtracted 1, and then I multiplied by the derivative of y with respect to x, right? Because that's exactly what this guy right here is. That's the derivative of y with respect to x. Okay, so I want you to remember that, because this is very, very important. So up here, when you're doing implicit differentiation, and I know that in this example it's relatively simple, so it doesn't maybe make too much sense, but what you want to remember is that y here is a function of x. So here we can write it explicitly. We're actually able to. Most problems you don't actually, you aren't able to write y explicitly as a function of x. So, but what you have to do is always pretend. You're not really pretending, but you always are assuming that y is a function of x. Okay, so let me go through the process of implicit differentiation. So let's say, for example, you have x squared plus y squared equals to 1. And you want to find the derivative and you want to find the tangent line. Whoa. At root 2, x equals root 2 over 2. Okay, so this is what you do. I'm going to write down the steps over here. Okay, so step 1, you're going to get the derivative of both sides. So I get the derivative of both sides, and then notice I'm using Leibniz notation. I'm using the operator for the derivative, and remember this guy tells me I'm getting the derivative with respect to x. So both the left side and the right side. Okay, now remember this guy right here, this is a function of x. So when I get the derivative of that guy, I'm going to have to use the chain rule just like I showed you up here. Okay, so step 2, you need to remember that you need to do the chain rule on y, and I'm going to emphasize y of x. So even though it's not written as y of x right here, we know it's a function of x. Okay, so we get the derivative of x squared. Now the derivative of x squared is just 2x, and that's it. Okay, and then plus y squared, the derivative of y squared is going to be 2y, but then you're going to multiply times the derivative of y with respect to x. So this is where I'm saying that, you know, you don't know what y is as a function of x, but you know that it is a function of x. So when you get the derivative of it, you have to use the chain rule, which means you bring down the 2, you leave the inside alone, so you leave the y alone, like we did right here, and then times the derivative of y, but since you don't know what it is, you symbolize it with dy over dx. So this right here, this dy over dx symbolizes, for example, this guy that we found right here. But remember, this time though, this dy over dx, that's what you're solving for. That's what you're looking for. So we're going to solve for this guy. Okay. So I know this is different than the way you're used to thinking about it, but go back and think about the chain rule connection, and it should make sense. Okay, so then on the right side, the derivative of the constant 1 is just 0. Okay, so then if I'm trying to solve for dy over dx, I'll move the 2x over. So I get dy over dx is equal to negative 2x. And then I'll divide both sides by 2y. Use a darker color. And so then what you get for dy over dx, so dy over dx, the derivative of y with respect to x, is equal to negative x over y. Okay, now notice that the formula for the derivative has both x's and y's, so that's okay. Okay, so we're done with the first part. And actually, I forgot to write down the third step. The chain rule, once we did the chain rule, we solved for dy over dx. And just to let you know, there's a shorthand notation for dy over dx. It's also commonly referred to as y prime. So sometimes you'll see this one as y prime instead of dy over dx. I like using dy over dx because then you're specifying it's clear that you're getting the derivative of y with respect to x, because there could be other variables around. Now, if I'm trying to find the tangent line at x equals root 2 over 2, well, the other thing I need is the y value. Now, the y value, in this case, I know it's also root 2 over 2, because if you go back, you know, my angle is pi over 4, so right here, this point is root 2 over 2 and root 2 over 2. Now, it's important to be given both the x and the y value, because notice that because it's not a function, and this happens almost every time in these problems, there's more than one y value for every x value. So we're specifying that it's positive root 2 over 2. Okay, so then what that means is that the slope, so now we're looking for the tangent line, so that means that the slope is equal to negative x, which is root 2 over 2, over y, which is root 2 over 2, and that's equal to negative 1. Okay, so here, step 4, since I'm finding the tangent line, so if you're looking for just dy over dx, you would be done. But here, if you're looking for the tangent line, then right here we continue with a couple extra steps. What I just did is I plugged it in to find the slope, plugged in my point, and then I'm just going to write down the usual, not a W, the usual steps. So we already know the steps. We find the slope, then we write down y equals to mx plus b. We plug in our slope, negative 1. We plug in our x value, root 2 over 2. Plug in our y value, root 2 over 2. And so if I solve for b, I get that b is equal to positive square root of 2. So then in the end, my tangent line is going to be y equals to negative 1 times x plus square root of 2. And if we go back to our picture, -1 square root of x plus square root of 2, that looks about right. So what we're saying is that the y-intercept would be square root of 2, and then the slope of this line is about, well, it is exactly -1. And that's it.